Hello, dear students. Now, let's begin with the calculation of field stabilization energy of octahedral complexes. Okay. Now, all of you know d orbitals splits into two orbitals, that is T2G and EG orbitals. Okay. Now, when these d orbitals are splitted and electron enter in the splitted orbital, there is total decrease in energy, and that energy is in energy called as crystal field stabilization, which in short is called as delta O, means octahedral, CFSE means crystal field stabilization energy. Crystal field stabilization for octahedral complexes is denoted by delta O. Now, when these electrons they enter into the splitted orbitals, either T2G or E, sometimes they get paired, and so when the electrons are paired, some pairing energy also involved, and that pairing is also added. Here you can see it stands for pairing energy. So pairing energy also added in the total of the CFEs. Now, crystal field stabilization for octahedral complexes is calculated by using the formula minus 2 by 5 m T2G plus 3 by 5 n Eg delta O plus LP. Here you can see m is number of electrons in T2G orbit, okay, while n is number of electrons in Eg orbital. L is number of electron pairs. I will explain. We will see when we will see some more problems, and E stands for the pairing energy. Now, you can see here why it is taken as a 2 by 5, because there are total 5d orbitals, okay, and there are 3 T2G orbitals, T2G orbitals and 2 EG orbitals, okay. These 3 T2G orbitals, their energies decrease as compared to 2 EG orbitals. So, it is taken as minus sign indicates decrease in energy, and it is taken as minus 2 by 5 m is number of electron in T2G orbitals plus 3 by 5 Eg, there are 2 Eg orbitals and their energy is as compared to 3 T2G orbitals. So, it is taken as plus 3 by 5 Eg delta O plus number of pairing electrons or number of paired electrons. Now, in place of minus 2 by 5, we can take minus 0.4 also, and in place of 3 by 5, we can take 0.6 also. 0.4 and 0.6 also. Here one thing you need to remember, delta O, it is equal to 10 d cube. So we can multiply this equation with 10, and when 0.4 is multiplied with 10, then it becomes 4, and 0.6 it is multiplied by 10, then it becomes 6. So it becomes quite easy for the calculation. Now calculate the crystal field stabilization of octahedral complexes. We will use this for, okay. Here m is number of electron in orbital, n is number of electron in orbital, and here this gets number of pairs of electron. Okay, now let's begin with, here This is the table which shows the crystal field stabilization energy and electron arrangement for octahedral complex. Okay. Side it is a strong field complex, that means low spin, and this side it is a weak field or high spin complex. So here now, sorry for the disturbances. Now here you can see for D1, D2 and D3, D1, D2 and D3, the CFSE value, it is same whether it is weak field or strong field. As I already told you, for D1, D2, D3 as well as for D8, D9 and D10, the distribution of electron in d orbital, it is same whether it is strong field ligand or weak field ligand. So in these cases, the value of CFSE, it is same. Okay. In case of D1, D2, D3, D8, D9 and D10. You can find out the difference only in case of D4, D5, D6 and D7. If the electrons, there are 4 electrons in d orbital, then in strong field or in low spin complexes, they are arranged like T2G4, EG0, and its CFSE after calculation you can find out it's a 16 DQ with 1 electron pair. But when 4 electrons, they are placed in weak field, they are distributed like T2G3, EG1, and there is CFSE is 6D. Similarly, in case of D5, it is 20 DQ with 2 pairing energy, while it is only 0 DQ in weak field ligand. While in similarly, you can find out for D6 and D7. Here, you should note that DQ for stronger field, DQ for stronger field is higher than the DQ for weak field. DQ for the weak field. Okay. So how these are calculated? By using the above formula that we will discuss in the next video.